Hello everyone. Today we'll study complex numbers. Complex numbers, they are also called imaginary numbers. What is an imaginary number? Let's look at equation first. How do we solve this equation? X squared minus 4 is equal to 0. When we try to solve this equation, I can first put f4 to both sides. Then I get x squared equal to 4. Next, I can take square root on both sides. When I take square root, answer could be either positive or negative square root of 4. When we take square root, always add plus or minus sign. Then we know that square root of 4 is 2. So x could be either positive 2 or negative 2. X could be either positive 2 or negative 2. They are both square root of 4. They are both square root of 4. 2 squared is 4. Negative 2 squared is also 4. They are both square root of 4. Since there are two square roots, we call the positive one the principal square root. We call the positive one the principal square root. The principal square root of 4. We call this positive 2 to be the principal square root of 4. Next, let's look at a different example. X squared plus 1 equal to 0. How can we solve this equation for x? For this equation, I can first of all subtract 1 from both sides. If I subtract 1 from both sides, I get x squared equal to negative 1. Now, can we find any real number x such that x squared equal to negative 1? It seems impossible because positive number squared is always positive, it won't be negative 1. Negative number squared, double negative is also positive, it won't be negative 1. So, there does not exist any real number x such that x squared equal to negative 1. Since there does not exist any real number x such that x squared equal to negative 1. Then we know that this equation doesn't have a real solution. If it has a solution, it must be imaginary number. If this equation has a solution, it must be an imaginary number. Then we know that the solution to the equation must be imaginary numbers. So we know that the solution to this equation must be imaginary numbers. Next, assume this equation has an imaginary solution. How can we find the imaginary solution here? In order to get x by itself, I can take square root on both sides. In order to get x by itself, I can take square root on both sides. If I take square root on both sides, I get x equal to positive or negative square root of negative 1. When we take square root, we need to always add positive and negative sign. That means x could be either positive square root of negative 1 or negative square root of negative 1. And we call a positive number to be, we call a positive square root of negative 1 to be principal square root. We call a positive square root of negative 1 to be the principal square root of negative 1. We call a positive square root of negative 1 to be the principal square root of negative 1. Next, based on this, let me introduce imaginary numbers. The first imaginary number is called the unit imaginary number. let I be the principal square root of -1. Then we know that I squared is -1. And I itself equal to square root of -1. This imaginary number I is called the unit imaginary number. Next, let me introduce complex number. A number in the form of a plus bi. A number in the form of a plus bi where a and b are real numbers. It's called a complex number. A number in the form of a plus bi, where a and b are real numbers, is called a complex number. And the form a plus bi is called the standard form of a complex number. The form a plus bi is called the standard form of a complex number. A number in the form of a plus bi, where a and b are real numbers, is called a complex number. And the form a plus bi is called a standard form of a complex number. So keep in mind that complex number in standard form always looks like this: a plus bi, where a, b are real numbers. Next, let me show you some examples. 7 plus 4i. That's in the form of a plus bi, where a is 7, b is 4. Since both a and b are real numbers, this is a real number. This is a complex number. And for this number, 3 minus 5i, it's in the form of a plus bi, where a equal to 3, b equal to -5. Since both a and b are real numbers, this is a complex number. This number, a half plus radical 3i, is also in the form of a plus bi, where a is a half, b is square root of 3. Since both a and b are real numbers, this is a complex number. Next example, -pi minus 2.5i. This number is also in the form of a plus bi, where a equal to -pi, b equal to -2.5. Since both a and b are real numbers, this is also a complex number. Next example, is this number 6i a complex number? 6i can be rewritten as 0 plus 6i. 6i can be rewritten as 0 plus 6i. It's also in the form of a plus bi, where a is 0, b is 6. Since both a and b are real numbers, 6i is a complex number. How about negative a? Is negative a complex number? We know that negative a is a real number. Is negative a complex number? Negative a can be rewritten as negative a plus 0 times I. Negative a can be rewritten as negative a plus 0 times I, and it's in the form of a plus bi, where a equal to negative a, b equal to 0. Since both a and b are real numbers, this is a complex number. Negative a is a complex number. So, all above numbers are complex numbers. Now here we see that for complex number there are two parts. That's called a real part, and that's called an imaginary part. Complex number has two parts. That's called a real part, and that's called an imaginary part. So let me introduce real part and imaginary part. Let a plus bi be a complex number in the standard form. Where a and b are real numbers. The real number a is called a real part of an imaginary number. The real number a is called a real part of an imaginary number, of a complex number. A is called a real part of the complex number. And the real number b here is called the imaginary part of the complex number. B is called an imaginary part of the complex number. And for example, in the previous examples, in the complex number 7 plus 4i, number 7 is the real part. And number 4 is the imaginary part. In the example 6i, number 0 is the real part, and number 6 is the imaginary part. Number 0 is the real part, and number 6 is the imaginary part. In negative a, in a complex number negative a is the real part, 0 is the imaginary part. In the complex number negative a is the real part. 0 is the imaginary part. Next, let me introduce real number and pure imaginary number. Real number and pure imaginary number. In a complex number, a plus bi, if the imaginary part if the imaginary part b is 0, then the complex number a plus bi equal to a. If b is 0, then a plus bi equal to a. It's called a real number. If the imaginary part b is 0, then a plus bi equal to a. It's called a real number. If the real part a is 0, then the complex number a plus bi can be written as bi. If a is 0, then a plus bi equal to bi. It's called a pure imaginary number. If a is 0, if the real part a is 0, then a plus bi equal to bi. That's called a pure imaginary number. Next, let me show you some examples. Real numbers looks like this. Number 2, number 1/3, square root of 5, 0.7. They are called real numbers. If there's no imaginary part, if the imaginary part is 0, that's called real numbers. And then for pure imaginary number looks like this. For example, 2i, the real part is 0. 1/3 times I, radical 5 times I, 0.7 times I, and so on. Those are called pure imaginary number. There's no real part. Those are called pure imaginary number. If there's no imaginary part, those are called real numbers. If there's no imaginary part, that's called real numbers. Next, let me introduce complex plane. What is a complex plane? Let's consider a plane which has two axes, a horizontal axis and a vertical axis. Consider a plane of two axes, horizontal axis and a vertical axis. If all real numbers are in the horizontal axis. If all real numbers are in the horizontal axis, we have 0 in the middle. Numbers to the right are positive. Numbers to the left are negative. And all pure imaginary numbers are in the vertical axis. All pure imaginary numbers are in the vertical axis. Pure imaginary number looks like this: I, 2i, 3i, 4i, 5i, and so on. Those are called pure imaginary numbers. Below 0, we have negative I, negative 2i, negative 3i, negative 4i, negative 5i, and so on. If we have all real numbers in the horizontal axis and all pure imaginary numbers in the vertical axis, this plane is called compressed plane. If we have all real numbers in the horizontal axis and all pure imaginary numbers in the vertical axis, this plane is called compressed plane. And every number in a compressed plane represents a compressed number. Every number in the compressed plane, every point in the compressed plane represents a compressed number. For example, point A, let me label some point. Point B, point C, point D, point E, point F. Every point in the compressed plane represents a compressed number. For example, in this example here, point A represents a compressed number 2 plus I. Point A represents a compressed number 2 plus I. Point B represents a compressed number negative 2 plus 4i. Point C represents a compressed number negative 5 minus 3i. Point C represents a compressed number negative 5 minus 3i. Point D represents a compressed number 1 minus 4i. D represents a compressed number 1 minus 4i. Point E represents number 4. Number 4 is also a compressed number, where the imaginary part is 0. Number 4 is also a compressed number. Point F represents number 3i. 3i is a pure imaginary number, which is also imaginary number. So every point in the compressed plane represents a compressed number. Every point in the compressed plane represents a compressed number. And also, every compressed number can be plotted in the compressed plane. Every compressed number can be plotted in the compressed plane. For example, plot each of the following compressed numbers in a compressed plane. Plot each of the following compressed numbers in the compressed plane. For example, g1 equal to 3 plus 4i. g2 equal to 2 minus 5i. g3 equal to negative 4 plus i. g4 equal to negative 3 minus 2i. g5 equal to number 3. g6 equal to 2i. g7 equal to negative 1. g8 equal to negative 3i. Let's plot its numbers in the compressed plane. in the complex plane, the horizontal axis represents the set of all real numbers. The vertical axis represents the set of all pure imaginary numbers. So for the horizontal axis, we have 0 in the middle, number to the right are positive, number to the left are negative. The vertical axis represents the set of all pure imaginary numbers. So number above 0 is I, 2i, 3i, 4i, 5i. Those are called pure imaginary number. Numbers below 0 are negative I, negative 2i, negative 3i, negative 4i, and negative 5i, and so on. Let's plot the first number. G1 is 3 plus 4i. 3 and 4i. 3 plus 4i is here. That's G1. 3 plus 4i. G2 is 2 minus 5i. Real number 2 is here. Negative 5i is here. 2 minus 5i is here. That's G2. 2 minus 5i. 2 minus 5i. That's G2. G3. Negative 4 plus i. Negative 4 plus I. G3 is here. Negative 4 plus I. That's G3. G4 is negative 3 minus negative 2. Negative 3 minus negative 2. Negative 3 is here. Minus negative 2 is here. That's G4. G4 is number 3. Number 3 is here. That's G5. Number 3 is here. This is G5. G6 is 2i. 2i is here. This is G6. G7 is negative 1. This is G7. G7 is negative 1. G8 is negative 3i. G8 is negative 3i, which is here. That's G8. So every complex number can be plotted in a complex plane, and every point in the complex plane represents a complex number. Next, let me introduce absolute values of complex numbers. We know that for real number x, its absolute value of x represents the distance from x to 0. For real number x, absolute value of x represents the distance from x to 0. For example, we have a number line. 0 in the middle, number to the right are positive, number to the left are negative. If I ask you, what's absolute value of 4? Absolute value of 4 represents distance from 4 to 0. Distance from 4 to 0 is 4. 1, 2, 3, 4. Distance from 4 to 0 is 4 units. So absolute value of 4 is 4. What's absolute value of negative 2? Absolute value of negative 2 represents distance from negative 2 to 0. From negative 2 to 0, the distance is 2 units. 1, 2. That's why absolute value of negative 2 is 2. Similarly, absolute value of 3 represents distance from 3 to 0. Distance from 3 to 0 is 1, 2, 3, 3 units. Absolute value of negative 5 represents distance from negative 5 to 0. Distance from negative 5 to 0 is 1, 2, 3, 4, 5. 5 units. That's why absolute value of negative 5 is positive 5. So that's how we find absolute value for real numbers. it represents the distance from the real number x to 0. And similarly, for complex number, absolute value means the same thing. It means the distance from the complex number to 0 in the complex plane. For complex number, usually we use z represent complex number. For complex number z, absolute value of z represent the same thing, the distance from z to 0 in the complex plane. Here, since z is a complex number, z is in the form of a plus bi. Since z is a complex number, z is in the form of a plus bi, where a and b are real numbers. Where a and b are real numbers. In the complex plane, the horizontal axis represents real numbers. The vertical axis represents pure imaginary numbers. So assume a is here. A is a real number, it's here. Assume bi is here. Bi is a pure imaginary number. Assume bi is here. Then that's the point a plus bi. That's the point z equal to a plus bi. Absolute value of z represent distance from z to 0. What's this distance? We know that distance from 0 to a is a. Distance from 0 to bi is b. Distance must be real number. So distance from 0 to bi is b. This side is a, this side is b, and these two sides form one right triangle here. In order to find distance here, we can use Pythagorean Theorem. In order to find distance here, we can use Pythagorean Theorem. Pythagorean Theorem says square root of z squared equal to a squared plus b squared. By Pythagorean Theorem, absolute value of z equal to square root of a squared plus b squared. So that's how we define absolute value of a complex number. So if z is a plus bi, its absolute value is always square root of a squared plus b squared. Next, let's look at some examples. Find each of the following absolute values. How do we find absolute value for the complex number 2 plus 7i? This is a complex number. For absolute value of a complex number, use the formula square root of a squared plus b squared, where a is the real part, b is the complex part. So that's square root of 2 squared plus 7 squared. Don't include i. Only use 2 and 7. Don't include i. 2 squared plus 7 squared. 2 squared is 4. 7 squared is 49. 4 plus 49 is 53. That's an absolute value of this complex number. Find absolute value for the number 4 plus ai. So use Pythagorean Theorem. 4 squared plus a squared. Use the real part square plus the imaginary part square. 4 squared is 16. A squared is 64. 16 plus 64 is 80. Now, can we simplify square root of 80? Square root of 80 can be rewritten as 16 times 5. Square root of 16 is 4. Square root of 5, leave it the way it is. So square root of 80 is 4 square root of 5. Next, how can we find absolute value of a number? Negative 3 plus 4i. How can we find absolute value of this complex number? Negative 3 plus 4i. Do the same thing. Use the formula a squared, square root of a squared plus b squared. So use negative 3 squared plus 4 squared. Negative 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. Square root of 25 is 5. So absolute value of this number, negative 3 plus 4i, is 5. Next, how can we find absolute value from a complex number? Negative 12 minus 5i. For negative 12 minus 5i, for any complex number, use this formula, a squared plus b squared, and take square root, where a and b, a is the real part, b is the imaginary part. So here I use negative 12 squared plus negative 5 squared. Negative 12 squared is positive 144. Negative 5 squared is 25. 144 plus 25 is 169. Square root of 169 is 13. That's an absolute value of this complex number, 12 minus 5i. Next, let me show you how to simplify complex numbers. First one, square root of negative 16. How can we simplify square root of negative 16? We know that there's no real numbers that multiply to itself equal to negative 16. So square root of 16 is not a real number. How can we simplify this complex number? Think of this. Square root of 16 can be rewritten as square root of 16 times negative 1. So it can be separated as square root of 16 times square root of negative 1. And we know that square root of 16 is 4. Square root of negative 1 is I. So the answer is 4i. Square root of negative 16 is 4i. Next one, how can we simplify square root of negative 25? Negative 25 can be written as square root of 25 times square root of negative 1. And we know that square root of 25 is 5. Square root of negative 1 is I. So the answer is 5i. Square root of negative 25 is 5i. Next, how can we simplify square root of negative 18? Square root of negative 18 can be written as square root of 18 times square root of negative 1. And 18 can be written as square root of 9 times square root of 2. Square root of 9 is 3. Square root of 2 cannot be simplified and leave it the way it is. Square root of negative 1 is I. So the final answer is 3 square root of 2 times I. That's how we simplify square root of negative 18. How about square root of negative 48? First of all, square root of negative 48 can be written as square root of 48 times square root of negative 1. And square root of 48 can be written as square root of 16 times square root of 3. Square root of 16 is 4. And I can leave square root of 3 the way it is. Square root of negative 1 is I. So the final answer is 4 square root of 3 times I. Next, how can we simplify square root of negative 75? Square root of negative 75 can be written as square root of 75 times square root of negative 1. Square root of 75 can be written as square root of 25 times square root of 3. And square root of 25 is 5. We cannot simplify square root of 3, leave it the way it is. And square root of negative 1 is I. So the answer is 5 square root of 3 times I. Next one. Square root of negative 27. Square root of negative 27 can be written as square root of 27 times square root of negative 1. And we know that square root of 27 can be written as square root of 9 times square root of 3. Square root of 9 is 3. And square root of 3, I leave it the way it is. Square root of negative 1 is I. So the answer is 3 square root of 3 times I. That's how we simplify square root of negative 27. Next, how can we simplify a plus square root of negative 20 over 4? Simplify the square root first. Simplify the square root first. Square root of negative 20, that can be done as square root of 20 times negative square root of negative 1. 20 can be written as 4 times 5. Square root of 4 is 2. We cannot simplify square root of 5, so leave it the way it is. Negative 1 is I. So here, we first of all simplify square root of negative 20. I get 2 square root of 5i divided by 4. Now observe, a, 2, and 4. Do they have any common factor? Observe these whole numbers, a, 2, and 4. We can see that their common factor is 2. For a, 2, and 4, their common factor is 2. I can divide all three numbers by 2. If I divide all three numbers by 2, I get 4 plus square root of 5i over 2. I divide all three numbers by 2. A divided by 2 is 4. 2 divided by 2 get cancelled. 4 divided by 2 is 2. That's how we simplify. A plus square root of negative 20 over 4. Next, how can we simplify? 12 minus negative 12 minus square root of negative 36 over 6. Again, simplify square root first. In a fraction, simplify square root first. Square root of negative 36 can be written as square root of 36 times square root of negative 1. Square root of 36 is 6, and square root of negative 1 is I. I get 12 minus 6i over 6. If I simplify square root of negative 36, I get 6i. Next, observe here. For 12, 6, and 6, both numerator is divisible by denominator. 12 divided by 6 is whole number 2. 6i divided by 6 is I. So that's the final answer. If it's divisible, take both numbers on the top, divide by the number on the bottom. If the numbers are not divisible, find their common factors, and then divide all numbers by the common factor. Next example, 10 plus square root of negative 44 over negative 12. So in a fraction, if we contain square root, simplify square root first. Square root of negative 44 can be written as square root of 44 times square root of negative 1. Square root of 44 can be written as square root of 4 times square root of 11. And we know that square root of 4 is 2. We cannot reduce square root of 11, so leave it the way it is. And square root of negative 1 is I. So if I simplify the square root, I get 2 square root of 11 times I. Over negative 12. Next, try to simplify this fraction. 10 and 12 is not divisible. 2 divided by 12 is also not divisible. If the numbers are not divisible, try to divide all three numbers by the greatest common factor. If the numbers are not divisible, divide all three numbers by their greatest common factor. For 10, 2, and 12, the greatest common factor is 2. So I can divide all three numbers by 2. 10 divided by 2 is 5. 2 divided by 2 get cancelled. I get square root of 11i. Negative 12 divided by 2 is negative 6. And for the final answer, if the denominator is negative, we try to make it positive. For the final answer, if the denominator is negative, we try to make it positive. So I can multiply the top and the bottom by -1. For the final answer, if the denominator is negative, try to make it positive. So I multiply the top and the bottom by -1. So the final answer is -5 minus -11i over +6. That's the final answer. Next, simplify the fraction. -4 minus square root of -52 over -2. Let's simplify the square root first. Square root of -52 can be written as square root of 52 times square root of -1. And we know that square root of 52 can be written as square root of 4 times square root of 13. Square root of 4 is 2. We cannot reduce square root of 13, so leave it the way it is. Square root of -1 is I. And plug in. We get -4 minus 2 square root of 13 times I over -2. Then let's try to divide. 4 divided by 2, that's divisible, we get whole number 2. 2 divided by 2 is also divisible, we get whole number 1. So, if they are both divisible by the denominator, take both numbers divided by the denominator. -4 divided by -2 is +2. -2 divided by -2 is +1. So you get positive square root of 13 times I. That's the final answer. Next, how can we simplify square root of -6 times square root of -14? How can we simplify square root of -6 times square root of -14? Be very, very careful. In general, if A and B are positive, square root of AB equals square root of A times square root of B. If A and B are positive, I can combine 2 square root into 1 square root if they are both positive. But if they are both negative, we cannot combine them. We cannot combine or separate if they are both negative. If A, B are both negative. Be very, very careful. Square root of AB doesn't equal to square root of A times square root of B. We cannot separate them or cannot combine them if A, B are both negative. In this case, -6 and -14 they are both negative. We cannot combine these 2 square root into 1 square root. We cannot combine these 2 square root into 1 square root if they are both negative. So what can we do here? Let's first of all rewrite the square root. Square root of -6 can be written as square root of 6 times I. Can be written as square root of 6 times square root of -1. Square root of 14 can be written as square root of 14 times square root of -1. And then we know that square root of -1 is I. Square root of -1 is I. Then I can put square root of 6 and square root of 14 together. Put I and I together, I get I squared. Here, 6 and 14, now they are both positive. I can combine 2 square root into 1 square root. If they are both positive, I can combine these 2 square root into 1 square root. I get square root of 84. 6 times 14 is 84 times I squared. How can we simplify square root of 84? 84 can be written as 4 times 21. Square root of 4 is 2, and we cannot reduce square root of 21, leave it the way it is. Here, square root of 84 is 2 square root of 24. What's I squared? I is square root of -1, so I squared is -1. I squared is -1. So the final answer is -2 square root of 21. And the final answer is -2 square root of 21. Next example. Square root of -3 times square root of -21. Since both numbers are negative, we cannot combine them together. Let's rewrite both numbers first. square root of negative 3 can be written as square root of 3 times square root of negative 1. Square root of negative 21 can be written as square root of 21 times square root of negative 1. And then we know that square root of negative 1 is I. Square root of negative 1 is I. Then put both square root together, I get square root of 3 times square root of 21. Put I and I together, I get I squared. Square root of 3 times square root of 21, that's square root of 63. I squared is negative 1. I squared is negative 1. Now, how can we reduce square root of 63? 63 can be written as 9 times 7. Square root of 9 is 3. And we cannot reduce square root of 7, leave it the way it is. So I get square root of 7, square root of 3 times square root of 7 times negative 1, which is negative 3 square root of 7. Next example, square root of negative 10 times square root of negative 15. When both numbers under square root are negative, we cannot combine the two square roots together. So simplify each square root first. Square root of negative 10 can be written as square root of 10 times square root of negative 1. Square root of negative 15 can be written as square root of 15 times square root of negative 1. And we know that square root of negative 1 is I. Square root of negative 1 is I. Together we have square root of 10 times square root of 15 times I squared. Now both numbers here are positive under the square root. I can combine these two square roots together, get square root of 150. When both numbers under the square root are positive, I can combine two square roots together, I get square root of 150. I squared is negative 1. Square root of 150 square root of 150 can be written as square root of 25 times square root of 6. 25 times 6 is 150. And we know that square root of 25 is 5. Square root of 6 cannot be reduced. We leave it the way it is. So I get 5 square root of 6 times negative 1. Together is negative 5 times square root of 6. Next, how can we simplify square root of negative 7 times square root of negative 70? When both numbers under square root are negative, we cannot combine these two square roots together. Let's simplify each number individually first. Square root of negative 7 can be written as square root of 7 times square root of negative 1. Square root of negative 70 can be written as square root of 70 times square root of negative 1. And we know that square root of negative 1 is I. Square root of negative 1 is I. Then both numbers under square root are positive. It can be written as square root of 7 times square root of 70. I times I is I squared. Since both numbers under square root are positive, I can combine these two square roots together. 7 times 70 is 490. I squared is negative 1. Square root of 490, it can be written as 49 times 10. Square root of 490 can be written as square root of 49 times 10. And we know that square root of 49 is 7. Since we cannot reduce square root of 10, I leave it the way it is. So square root of 490 can be reduced as 7 square root of 10, and then times negative 1. 7 square root of 10 times negative 1 is negative 7 square root of 10. Next example, square root of negative 13 squared. When we see square root of negative 13 squared, that means square root of negative 13 times itself. Square root of negative 13 can be written as square root of 13 times square root of negative 1. Square root of negative 13 is square root of 13 times square root of negative 1. And then we know that square root of negative 1 is I. Square root of 13 times square root of negative 1. Square root of negative 1 is I. If we multiply, we have square root of 13 times itself, and I times itself. I times I is I squared. Since 13 is a positive number, square cancel square root, we get positive 13. I squared is negative 1. 13 times negative 1 is negative 13. Next example, square root of negative 11 square. So when we see square root of negative 11 square, that means square root of negative 11 times itself. Since both numbers under square root are negative, it can be rewritten as square root of 11 times square root of negative 1 times square root of 11 times square root of negative 1. And we know that square root of negative 1 is I. Square root of negative 1 is I. Square root of 11 times square root of 11 is square root of 11 squared. I times I is also I squared. Since 11 is a positive number, square cancels square root, we get 11. I squared is negative 1. 11 times negative 1 is negative 11. Next example, square root of negative 15 squared. So when we see square root of negative 15 squared, write it twice. Write as square root of negative 15 times itself. And then square root of negative 15 can be written as square root of 15 times square root of negative 1. Square root of 15 times square root of negative 1. Same thing, square root of negative 15 can be written as square root of 15 times square root of negative 1. And we know that square root of negative 1 is I. Square root of negative 1 is I. Together, we have square root of 15 times itself, which is square root of 15 squared. I times I is I squared. Since 15 is a positive number, square cancels square root, we get 15 by itself. I squared is negative 1. 15 times negative 1 is negative 15. Next, square root of negative 17 squared. When we have square root of negative 17 squared, run the same thing twice. That's square root of negative 17 times itself. And we know that square root of negative 17 can be written as square root of 17 times square root of negative 1. Square root of negative 17 can be written as square root of 17 times square root of negative 1. And we know that square root of negative 1 is I. Square root of negative 1 is I. Then together, square root of 17 times square root of 17 is square root of 17 squared. I times I is I squared. 17 is a positive number, so we have square cancel square root. We get 17 by itself. I squared is negative 1. 17 times negative 1 is negative 17. Next, let me show you addition and subtraction of complex numbers. How can we add complex numbers? For example, we have two complex numbers, a plus bi plus c plus di. How can we add these complex numbers? So when we try to add complex numbers, we can first of all drop parentheses. Write it as a plus bi plus c plus di. Then we put the real part together and put the imaginary part together. If I put the real part together, I get a plus c. If I put the imaginary part together, I get bi plus di. Then in the second part, I can factor I out. In the second part, I can factor I out. If I pour I get I times b plus d. And in general, we put I in the back. In general, put I in the back. We get a plus c times b plus d times I. That's how we add complex numbers. So we have a plus c plus b plus d I. That's how we add complex numbers. That's how we add complex numbers. How about subtraction? How can we subtract complex numbers? Suppose we have a plus bi minus c plus di. How can we subtract complex numbers? Do the same thing. Try to eliminate parentheses first, then combine the real part and the imaginary part together. So a plus bi leave it the same. When there's subtraction in the form, consider this is -1. If I distribute -1, I get -c minus di. Then put the real part together and put the imaginary part together. The real part here is a and c. Put it together, I get a minus c. Then put the imaginary part together. We have bi minus di. For bi minus di, I can factor here. I is a common factor, I can pull I. If I pull I get b minus d. In general, put I in the back. In general, put I in the back. So the final answer is a minus c plus b minus d times I. So when we subtract two complex numbers, I get a minus c plus b minus d times I. That's how we subtract complex numbers. So for addition and subtraction, try to eliminate the parentheses first, then combine the real part and imaginary part together. That's how we add and subtract complex numbers. Next, let me show you some examples. First example, 4 plus 7i plus 3 plus 5i. I can first of all eliminate the parentheses. So I got 4 plus 7i plus 3 plus 5i. Then I can combine like terms. 4 plus 3 is 7. 7i plus 5i, if I combine like terms, that's 12i. So that's how we add complex numbers. Next example, -2 plus ai plus -5 minus 2i. I can first of all eliminate the parentheses. I get -2 plus ai plus -5 is the same as -5 plus -2i. Then combine like terms. -2 plus -5 is -7. ai minus 2i is 6i. That's how we add complex numbers. Next example, 3 minus 4i minus 5 minus 2i. Same thing, I can first of all eliminate parentheses. I get 3 minus 4i. When we see subtraction, consider this is a negative sign. If I distribute negative sign into the parentheses, I get -9, double negative is positive, plus 2i. Consider this negative sign. Consider this is subtraction as a negative sign. If I distribute, I get -9. Double negative is positive, I get positive 2i. Then combine like terms. 3 plus -9 is -6. -4i plus 2i is -2i. -4i plus 2i is -2i. That's how we subtract complex numbers. Next example, -1 minus 7i minus -4 plus 6i. Same thing, first of all, try to eliminate parentheses. I get -1 minus 7i. When we see subtraction, consider this as a negative sign. If I distribute negative sign, double negative is positive, I get +4. Negative times positive is negative. I get -6i. Then combine like terms. -1 plus 4 is +3. -7i minus 6i is -13i. That's how we subtract complex numbers. Next, let me show you the multiplication of complex numbers. How can we multiply complex numbers? A plus bi times c plus di. When we multiply two complex numbers, we can try to distribute and combine like terms. If I distribute, I get ac plus ad, adi, ac plus adi, plus bci plus BDI squared. Distribute first, then simplify. AC stays the same. ADI, BCI stays the same. Here, I squared is -1. I squared is -1. -1 times BD is -BD. Then we put a real number together. AC and BD, they are real numbers. Put a real number together, we get AC minus BD. Put a real number together, and then put the imaginary part together. Put the real part together, and put the imaginary part together. If I put the imaginary part together, I get ADI plus BCI. For the imaginary part, I can pull out common factor I. For the imaginary part, I can pull out a common factor I. If I pull out I get I times AD plus BC. In general, we put I in the back. In general, put I in the back. So the final answer is AC minus BD plus AD plus BC times I. That's how we multiply complex numbers. A plus BI times C plus DI. The answer is AC minus BD plus AD plus BC times I. That's how we multiply complex numbers. Next, let me show you some examples. 2 plus 7i times 3 minus 6i. I can first of all distribute. 2 times 3 is 6. 2 times negative 6i is negative 12i. 7i times 3 is 21i. 7i times negative 6i is negative 42i squared. Then simplify. I can combine like term first. Negative 12i plus 21i, that's positive 9i. And we know that I squared is negative 1. Negative 42 times negative 1 is positive 42. Then combine like terms. 6 plus 42 is 48. So the final answer is 48 plus 9i. Next example. 4 minus 2i times negative 1 minus 3i. When we multiply two complex numbers, we need to distribute first. 4 times negative 1 is negative 4. 4 times negative 3i is negative 12i. Negative 2i times negative 1 is positive 2i. Negative 2i times negative 3i is positive 6i squared. Next, I can combine like terms. Negative 12i plus 2i is negative 10i. I squared is negative 1. Positive 6 times negative 1 is negative 6. Then combine like terms. Negative 4 plus negative 6 is negative 10. So the final answer is negative 10 minus 10i. Next example. 5 minus I times 6 plus I. So let's distribute first. 5 times 6 is 30. 5 times I is 5i. Negative I times 6 is negative 6i. Negative I times I is negative I squared. Negative I times I is negative I squared. Then we can combine like term first. 5i minus 6i is negative 1i. 5i minus 6i is negative 1i. Minus I squared. I squared is negative 1. And double negative is positive. Get plus 1. Combine like terms. 30 plus 1 is 31. Final answer is 31 minus I. Next example. Negative 2 minus 3i times negative 4 plus 9i. When we multiply two complex numbers, we can distribute first. Negative 2 times negative 4 is positive 8. Negative 2 times positive 9i is negative 18i. Negative 3i times negative 4 is positive 12i. Negative 3i times 9i is negative 27i squared. Then we can combine like terms first. Negative 18i plus 12i is negative 6i. Minus 27 times I squared. We know that I squared is negative 1. Then negative 27 times negative 1 is positive 27. Then we combine like terms. A plus 27 is 35. So we get 35 minus 6i. That's the final answer. Next. 2i times negative 3 minus 5i. 2i times negative 3 minus 5i. Same thing, we can distribute first. 2i times negative 3 is negative 6i. 2i times negative 5i is negative 10i squared. And we know that I squared is negative 1. Negative 10 times negative 1 is positive 10. In general, for the final answer, we'll try to put it in the standard form, which means put it in the form of a plus bi. For the final answer, try to put it in the standard form. A plus bi, which means the real part comes first, and then imaginary part comes after. So write the real part first. 10 minus 6i. That's the final answer in the standard form. Next. Negative 3i times negative 2 plus 7i. We can distribute first. Negative 3i times negative 2 is 6i. Negative 3i times 7i is negative 21i squared. We know that I squared is negative 1. Negative 21 times negative 1 is positive 21. Then, for the final answer, put it in standard form, which means the real part comes first. We get 21 plus 6i. That's the final answer. Next example. 2 plus I squared. 2 plus I squared, it means 2 plus I times 2 plus I. Then when we multiply two complex numbers, we can distribute first. 2 times 2 is 4. 2 times I is 2i. I times 2, that's another 2i. Then plus I times I, that's I squared. Then we can combine like terms first. 2i plus 2i is 4i. And we know that I squared is negative 1. Combine like terms. 4 plus negative 1 is 3. So the final answer in the standard form is 3 plus 4i. Next. 3 minus 5i squared. When we have square, we take the complex number, multiply to itself. 3 minus 5i times 3 minus 5i. And when we multiply two complex numbers, we can distribute first, then combine like terms. If I distribute, 3 times 3 is 9. 3 times negative 5i is negative 15i. Negative 5i times 3, that's another negative 15i. Negative 5i times negative 5i, that's positive 25i squared. Then we can combine like terms first. If I combine like terms, negative 15i plus negative 15i is negative 30i. And I squared is negative 1. We get 9 minus 30i. 25 times negative 1 is negative 25. If I combine like terms, 9 plus negative 25 is negative 16. And leave 30i the same. That's the final answer to this. Next, let me show you the division of complex numbers. How can we divide two complex numbers? For example, we have a plus bi divided by c plus di. How can we divide two complex numbers? The division of complex numbers is a little tricky. We can divide these two numbers directly. Before I show you the division, let me introduce conjugate first. Before I show you division, let me introduce conjugate first. What's called conjugates? Complex numbers a plus bi and a minus bi. They are called conjugates of each other. They are called conjugates of each other. For two complex numbers, if the real part looks exactly the same and the imaginary part is an opposite, then they are called conjugates of each other. If the real part looks exactly the same and the imaginary part is the opposite, then these two complex numbers, they are called conjugates of each other. For example, 2 plus 3i and 2 minus 3i, they are conjugates of each other. The real part looks exactly the same. The imaginary part is an opposite of each other. So they are conjugates of each other. Another example, -4 minus 5i and -4 plus 5i. They are also conjugates of each other because the real part looks exactly the same and the imaginary part is an opposite of each other. They are also called conjugates of each other. Now, let me show you the division. We can divide two complex numbers directly, but if we want to do division here, we multiply this fraction, both the top and the bottom, multiply both top and the bottom by the conjugate of the denominator. We multiply both top and the bottom by the conjugate of the denominator. The conjugate of the denominator here is c minus di. The real part looks exactly the same. The imaginary part has opposite sign. So, multiply the conjugate of the denominator to both the top and the bottom. Then, if we distribute, on the numerator, I get AC minus ADI plus BCI minus BDI squared. That's the numerator. In the denominator, if we distribute, I get C squared minus CDI plus CDI minus D squared times I squared. And then we know that I squared is -1. I squared is -1. So in the numerator, I get AC minus ADI. AC minus ADI minus plus BCI. Negative BD times -1 is positive BD. In the denominator, we get C squared. Negative CDI plus positive CDI get cancelled. Times negative minus D squared times -1. I squared is -1. Negative D squared times -1 is positive D squared. Then in the numerator, we put the real number, put the real part together, and put the imaginary part together. If I put the real part together, I get AC plus BD. If I put the imaginary part together, let me run the positive number first. I get BCI minus ADI. I write positive term first, so I get BCI minus ADI. That's the numerator. Denominator is C squared plus D squared. Then continue. In the second term here, I can pull out I. In the second term here, I is a common factor, I can pull out I. If I pull out I, first part stays the same, AC plus BD. In the second part, if I pull out I, write I in the back, I get BC minus ADI. BC minus AD times I. In general, write I in the back over C squared plus D squared. Then, for the final answer, we try to in the standard form of complex numbers, put it in the form of A plus BI. For the final answer, try to write a complex number in the standard form, A plus BI. For the final answer, try to put a complex number in the standard form, A plus BI. So what we can do is take the real part, divide by the denominator, and the imaginary part, divide by the denominator. If I take the real part, divide by the denominator, I get AC plus BD over C squared plus D squared. Then put the imaginary part, divide by the denominator. I get BC minus AD over C squared plus D squared times I. That's the final answer in the standard form. So the division here, A plus BI divided by C plus DI. The final answer is AC plus BD over C squared plus D squared plus BC minus AD over C squared plus D squared I. That's the division of complex numbers. That's the division of complex numbers. Next, let me show you some examples. How can we divide complex numbers? 4 plus 3i over 1 plus 6i. When we try to divide complex numbers, first of all, multiply both top and bottom by the conjugate of the denominator. Conjugate means the real part is exactly the same. Real part stays the same. For the imaginary part, change the sign. Positive 6 become negative 6. Then multiply the same thing to the top and the bottom. Then we can distribute. In the numerator, distribute. 4 times 1 is 4. 4 times negative 6i is negative 24i. 3i times 1 is 3i. 3i times negative 6i is negative 18i squared. That's the numerator. For the denominator, 1 plus 6i times 1 minus 6i. There's a formula that says a plus b times a minus b. That always equal to a squared minus b squared. When we have a plus b times a minus b, we always have a squared plus b squared. This formula is called difference of perfect squares. A squared minus b squared is always a plus b times a minus b. So if we apply this formula here, treat this as a, this as b. We have a plus b times a minus b. Apply the formula, we have 1 squared minus 6i squared. That's the denominator. Then simplify both top and bottom. If we simplify the top, 4 stays the same. Combine like terms. Negative 24i plus 3i is negative 21i. I squared is negative 1. So we get negative 18 times negative 1. In the denominator, 1 squared is 1. 6 squared is 36. I squared is negative 1. Distribute square to each of them. 6 squared is 36. I squared is negative 1. Then simplify. In the top, negative 18 times negative 1 is positive 18. Positive 18 plus 4 is positive 22 minus 21i. In the denominator, negative 36 times negative 1 is positive 36. So we get 22 minus 21i over 37. Then for the final answer in the standard form, we take both terms on the top, divide by the bottom. I get 22 over 37 minus 21 over 37i. That's the final answer in the standard form. Next example, 2 minus 3i over 4 minus i. When we try to divide two complex numbers, we can divide this number directly. So find the conjugate from the denominator first. Find the conjugate from the denominator first. For the conjugate, the real part stays the same. The imaginary part is the opposite. For positive I, the opposite is, for negative I, the opposite is positive I. For negative I here, its opposite is positive I. Then multiply this conjugate to both the top and the bottom. Multiply the same thing to the top and the bottom. So multiply 4 plus I to both top and the bottom. Then from the top, we can distribute. If we distribute, 2 times 4 is 8. 2 times I is 2i. Negative 3i times 4 is negative 12i. Negative 3i times I is negative 3i squared. That's the numerator. In the denominator, apply the difference of perfect squares. We have 4 squared minus I squared. Then simplify both top and bottom. In the top, if we combine like terms, 2i minus 12i is negative 10i. I squared is negative 1. That's the numerator. In the denominator, 4 squared is 16. I squared is negative 1. Then combine like terms. In the numerator, negative 3 times negative 1 is positive 3. A plus positive 3 is 11. We get 11 minus 10i in the numerator. In the denominator, double negative is positive. 16 plus 1 is 17. Then, for the final answer, try to put it in the standard form. So I take both parts on the top, divide by the part on the bottom. 17 over 11 over 17, that's the real part. 10 over 17, that's the imaginary part. I stays the same. 11 over 17, that's the real part. 10 over 17, that's the imaginary part. I stays the same. That's the answer to this division. Next example. 3 minus 7i over 6 plus 2i. 3 minus 7i over 6 plus 2i. When we try to divide two complex numbers, find the conjugate from the denominator first. So for the conjugate, the real part stays the same. The imaginary part will be the opposite of this number. Opposite of 2i is negative 2i. That's the conjugate of the denominator. Then multiply the conjugate to both the top and the bottom. Multiply 6 minus 2i to both the top and the bottom. Then for the top, distribute. 3 times 6 is 18. 3 times negative 2i is negative 6i. Negative 7i times 6 is negative 42i. Negative 7i times negative 2i is positive 14i squared. That's the numerator. In the denominator, apply the formula of perfect squares. We have 6 squared minus 2i squared. Then combine like terms on the numerator. Negative 6i minus 42i is negative 48i plus 14i squared. I squared is negative 1. On the denominator, 6 squared is 36 minus 2 squared, distribute square, 2 squared is 4. I squared is negative 1. Then simplify, combine like terms. On the numerator here, 14 times negative 1 is negative 14. 18 minus 14 is 4. Minus 48i. That's the numerator. In the denominator, negative 4 times negative 1 is positive 4. 36 plus 4 is 40. That's the denominator. Numerator will 4 minus 48i. Then, for the final answer in the standard form, take both number on the top, divide by the number on the bottom. Okay, 4 over 40 minus 48 over 40i. If I reduce the fraction here, for 4 over 40, I can divide both number on the top and the bottom by 4. I get 1 over 10. If I divide both number by 4, I get 1 over 10. For the second fraction, I can divide both number by 8. 48 divided by 8 is 6. 40 divided by 8 is 5. I get 6 over 5i. That's the final answer for this division here. Next example. 5 plus I over 2 minus 5i. We're going to divide two fractions. We're going to divide two complex numbers. First of all, find the conjugate from the denominator first. The conjugate of the denominator, we first of all keep the real part the same. For the imaginary part, we choose an opposite. The opposite of negative 5i is positive 5i. That's the conjugate of the denominator. Multiply this number to both top and bottom. Get 2 plus 5i. Then multiply the top and the bottom. If we multiply the top, we can distribute. 5 times 2 is 10. 5 times 5i is 25i. I times 2 is 2i. I times 5i is 5i squared. That's the numerator. For the denominator, we can apply the formulas of perfect square. That's 2 squared minus 5i squared. That's the formula of difference of perfect squares. Then simplify the top and the bottom individually. For the top, we can combine like term first. 25i plus 2i is 27i. Plus 5i squared. We know that I squared is negative 1. On the denominator, 2 squared is 4. Minus, for the second term, distribute square to each of them. 5 squared is 25. I squared is negative 1. On the numerator, I get 10 plus 27i. 5 times negative 1 is negative 5. On the bottom, negative 25 times negative 1 is positive 25. If I combine like terms on the numerator, 10 minus 5 is 5 plus 27i. On the denominator, 4 plus 25 is 29. Then we must find the final answer in the standard form, which means I take 5 divided by 29. And then I take 27 divided by 29. Leave I the way it is. That's the final answer in the standard form. Next example. 2 divided by 3 minus I. 2 divided by 3 minus I. So when we try to divide two complex numbers, we first of all find the conjugate of the denominator. What's the conjugate of 3 minus I? For the conjugate, we first of all keep the real part the same. For the imaginary part, take the opposite. For negative I, its opposite is positive I. So multiply 3 plus I to both the numerator and denominator. Then multiply both top and bottom individually. For the top, I can distribute 2 first. If I distribute 2, I get 6 plus 2i. 2 times 3 is 6. 2 times I is 2i. For the denominator, Apply the formulas of difference of perfect squares. I get 3 squared minus I squared. Then, if I simplify the denominator, 3 squared is 9. I squared is -1. 9 minus -1, double negative is positive. 9 plus 1 is 10. Then, for the final answer in the standard form, I take 6 divided by 10 plus 2 divided by 10i. And then, for 6 divided by 10, I can divide top and bottom by 2. Make it 3 over 5. For 2 divided by 10, I can divide top and bottom by 2. Make it 1/5. So the final answer is 3/5 plus 1/5 I. That's the final answer in the standard form. Next example, -5 divided by 2 plus 3i. So when we try to divide complex numbers, first step, find the conjugate from the denominator first. For the conjugate of the denominator, the real part stays the same. For the imaginary part, take the opposite. For positive 3i, the opposite is -3i. So this is the conjugate of the denominator. Next, multiply the conjugate to both the numerator and denominator. Then multiply. Multiply the top and the bottom individually. For the top, -5 times 2 is -10. -5 times -3i is positive 15i. That's the numerator. For the denominator, apply the formula of difference of perfect squares. I get 2 squared minus 3i squared. Then leave the top the same. -10 plus 15i. For the denominator, 2 squared is 4. For the second term, distribute square. 3 squared is 9. I squared is -1. -9 times -1 is positive 9. 4 plus 9 is 13. Then for the final answer in the standard form, we write -10 over 13 plus 15 over 13i. That's the final answer in the standard form. Next example, 7 minus 4i over 2i. That's a very special case. If the denominator only has one term of I, we multiply both top and bottom by I. If the denominator only has one term of I, multiply both top and bottom by I. That's a very special case. If the denominator only has one term of I, multiply both top and bottom by I. If I multiply I to the numerator, I get 7i minus 4i squared. Distribute I to both of them. I get 7i minus 4i squared. That's the numerator. For the denominator, 2i times I is 2i squared. Then simplify. We know that I squared is -1. If we multiply, we have 7i plus 4 over 2 times -1 is -2. Then for the final answer, write the real part in the front. For the final answer, write the real part in the front. We write 4 plus 7i on the numerator. Denominator is -2. And then for the final answer in the standard form, take both the numerator divided by the denominator. 4 divided by -2. That's the real part. Plus 7 divided by -2. That's the imaginary part. And then simplify. 4 divided by -2 is -2. 7 divided by -2 is -7 over 2i. That's the final answer in the standard form. Next example, 6 plus 5i over -4i. If the denominator only have one term of I, we multiply both top and bottom by I. If the denominator only have one term of I, we multiply both top and bottom by I. In the top, we distribute I to both terms, because we get 6I plus 2I squared, distribute I. 6I plus 2I squared, that's the numerator. For the denominator, negative 4I times I is negative 4I squared. Negative 4I times I is negative 4I squared. Then simplify. We know that I squared is negative 1. I squared is negative 1. In the numerator, we get 6I minus 2. 2 times negative 1 is negative 2. In the denominator, negative 4 times negative 1 is positive 4. And then in general, we write the real part first. Write the real part in the front. Put the imaginary part in the back. So numerator can be rewritten as negative 2 plus 6I. Then over 4. Next, take both terms in the top, divide by the term on the bottom. We get negative 2 over 4 plus 6 over 4I. Then simplify the fractions. Negative 2 over 4, I can divide top and bottom by 2, which is negative 1 over 2. And for 6 over 4, I can divide top and bottom by 2. I get 3 over 2I. That's the final answer in the standard form.